Hello, my name is Brad Guerin. I am the lead imagery software engineer with Travelers Insurance's Artificial Intelligence Accelerator. So we're the department within Travelers Insurance that works to drive better outcomes for our customers using artificial intelligence, using data science. And I'm excited to be virtually here today. I know it's not the normal experience that folks would be used to at Dev Summit, and it's a blessing and a curse. Certainly the curse is that I'm looking out my window at snow right now instead of beautiful Palm Springs. But the blessing is if this turns out to be a horrible presentation, I don't get to see folks, step up and walk out of the room. So I guess that's my blessing in the end. But I do hope that you find value out of this. And again, thank you for watching. So briefly, I am going to talk about using Esri and an architecture for real-time presentation of machine learning evaluations. So what does that mean? That means using ArcGIS technologies within larger architectures, which often incorporate open source tools to drive better customer outcomes and really bring more folks into the fold. Because if nothing else, I'd love to kind of preach and proselytize the value of working in cross-functional teams and working as partners with folks within our organizations. Many times in the past, if you've been a GIS developer long enough, and often in organizations this is still the model, we work in very transactional ways, right? So other folks from our organization come to us, they need a map, they need an interface built, they ask us to do that, we build it for them, and we move on like they're our internal customer. But we can often achieve more and help to drive those organizations that we work with further by working as partners with those around us, with traditional software development teams or with data scientists. So I'm going to talk a bit about more and a success story of how that can really drive a place forward. So importantly, the work that I'm going to talk to you about today was the result of a cross-functional team. So data scientists were involved, GIS developers were involved, data engineers were involved. And really, it's that culmination and that working together, which not only helps to create a great product, but it also necessitates kind of thinking outside of the box and bringing in other ways to approach problems. Because data scientists, especially if they haven't experienced Esri tools before, are more inclined to use open source tools, and it's often a challenge for us to incorporate those open source tools within the larger stacks, development stacks that we're working in. So I'm going to talk about today the creation of a product that I think a lot of folks and a lot of players in the industry are doing something similar now. We actually approached this problem a few years ago, and it was pretty groundbreaking at the time, and we garnered a couple industry awards for doing so, and it was an exciting way to create value for our customers and really be partners for our external customers, folks that have travelers insurance, especially in California, where there is that risk of wildfire, especially as climate change increases. And so the name of this project was Wildfire Total Loss Identification. So the business problem was that our insured in California, in other areas, in other Western states where the risk of wildfire is very high, are often evacuated from areas where these wildfires happen. And wildfire intensity and the breadth of wildfires continues to increase in the West. So we're always looking for ways to be better partners with the folks that have travelers insurance. And one of the ways that we do so is by responding better to their needs when they are evacuated from their homes and when they don't have access to see the extent of the damage that's been done. So what we did is leveraging after-event imagery from aerial imagery vendors, we approached this business problem, and representatives at our National Catastrophes Center, which is this wonderful center that Travelers has that focuses on these catastrophic events. So whether it be hurricanes, wildfires, they are spending hours and hours working towards understanding weather patterns, understanding where they need to deploy resources to. So partnering with them and working with them, we targeted in an area where we can provide a better way to provide service to our customers. And that way was by prioritizing which properties representatives look at first. We can actually help them to spend less time sifting through image after image and poring over the aerial imagery as it comes through and kind of scrolling through a map. And by doing so, this allows us to reach out to our customers and call them oftentimes before they can even get back to their house and start to make those initial payments so that they can pay for the hotels that they're staying in, or pay for other expenses that have come out of being evacuated from their homes. So this is it really is a great success story. But even though it is a great success story, there's challenges that come out of that. There's development problems that come out of that. So traditional data science relies on data which is often, it's coming in at known times and it's coming in at known formats with no spatial component about it. So not only did the development team here need to work with the fact that the data that we were getting was coming in at unknown times, but we also needed a way to provide user input so that user could be connected. Those users in the National Catastrophe Center could be connected to where a model was run and what region of the country and when it was run. So when imagery does come in, when are we going to run that model? We don't necessarily have feedback on when the model should be run. So there's not a cron job that can be triggered. And really, one of the more important things and one of the more challenging is that our business users desired near real-time output from the model. So they wanted to be able to trigger these runs of the model and then have them presented to them in real time. So the first challenge here, and I know that every data scientist, every data engineer, and every GIS practitioner out there has heard this a million times, that is garbage in, garbage out. So as we look to train a model, it's important to, really create a unified picture of what that data could be and produce one single input that the model could work with and have that be standardized. So how did we do that? So first, the number one step was to identify the roof center points. So by taking footprints of the roof, you could distill that down and create roof center points, those centroids. You could then use square buffers around those center points to extract the images and then tag each one of those, knowing that you were getting a very regular image. So it was standardized to X number of pixels by X number of pixels, and the model could be trained knowing that and thereby create a better result in the end. But this is easier said than done, and it creates a large challenge, right? So in California, there's millions of footprints, and distilling millions of footprints into centroids, of course, with a local machine, the moment that you try to load that and run the function to create those centroids, the volume of data is prohibitively large. It causes a RAM outage, and it crashes the machine almost instantly. So that doesn't necessarily work. One of the greatest aids here was to be able to use Esri's GIS tools for Hadoop. So by creating well-known text representations of all of the buildings in the state of California, we could then almost momentarily, in a matter of seconds, distill those footprints into those centroids. Because using Hadoop, using that distributed computing, it allows the function which creates those centroids to be spread across multiple machines and multiple memory. So within moments, within seconds, 6 million footprints could be distilled. So it was a really powerful ally in this. But this success story is really only part of the picture, and I really want to spend a lot more time talking about that microservice approach to delivering Esri tools, so some of those spatial functions. And so that brings me to challenge number 2. Real time it's real fast. So being able to deliver model results in real time becomes a challenge for a development team. So what we did here is we took a new approach to models and putting the parameters in the user's hands really allowed us to deliver that interface which could solve the problems that they had, and being able to run the model where they wanted to. So traditional data science, there's a known data availability, whether you're accessing it from tables which have been pre-processed, whether you're accessing rasters or images that have already been downloaded, and you know where they are and when they are. There's no geographic component involved quite often. And it can be executed on a predictable time series. So all of these things work together to enable those batch and cron jobs so that the user can access the data at a known time. So say this job runs overnight, the user can come in the next morning and have that output data available to them. In the catastrophe image analysis, this isn't necessarily the case. So catastrophic fires can happen at any time. The extent of the fire or the imagery captured is unknown. So a fire can happen anywhere. It can be of any extent. And, within that extent, there may be certain areas that are more damaged than others, which necessitates flying to get aerial image in those areas rather than others. The time to put those birds in the air to collect the aerial imagery, of course, is not a known factor, as well as the processing time. So between when the wheels land on the runway to when that data is available in a console or a REST endpoint, that's completely unknown. And then finally, there is just all of these put together just creates this necessity for a GUI-based, graphic user interface-based way to trigger a model and control where the model is run and when it is run. So kind of our first attempt here was to approach this fully within the ArcGIS Enterprise ecosystem. So what does that mean? That means creating a geoprocessing service using ArcGIS Pro and publishing that to ArcGIS Server, and then creating a web app builder interface on top of those geoprocessing services that are created. That, of course, was not without its challenges. There are trade-offs when using web app builder or when using geoprocessing services. And these are considerations that you need to take when building within that. So the benefit, the out-of-the-box stability and logging from these geoprocessing services and web app builder as well is really second to none. And web app builder, especially, you can stand up a front-end interface in lightning fast times. And many times that allows you to just bring a solution to your customer much faster. And it's approachable and maintainable for a broad level of coding experience. What Esri has done with Web App Builder and with geoprocessing services can't be understated when it comes to democratizing the ability to publish these services, these REST endpoints, and these user interfaces. But there are trade-offs when it comes to that. So quite often interactions with open source Python packages, some of the more powerful ones, some of the more data science focused ones can be unpredictable. It's a complicated implementation pattern, and there is limited capability to multi-thread geoprocessing services, because quite often that relies on recreation of the entire environment that a process is being run in. So you'll often see, if you try to multi-thread out of the box with ArcGIS Pro, it will spin up over and over again instances of ArcGIS Pro to recreate that entire stack. Monolithic architectures can be difficult to reuse in pieces, and that's important to keep in mind. Kind of the way that the world of architecture is moving is away from those monolithic architectures and towards a more microservice-based approach. And of course, Web App Builder does limit flexibility on the front end. So while you may gain the ability to have a low-code, no-code solution for your front end and be able to create it very rapidly, there isn't that 100% flexibility that you may gain by creating a JavaScript interface yourself. So what is meant by microservice architectures? Folks may not have encountered those before, so I think it really bears just a brief high-level overview to understand them. So the important part of a microservice architecture is to break down these constituent pieces, the smallest pieces of functionality that your application can deliver, and and deliver those via endpoints to either applications, to web interfaces. And by doing so, you allow reusability. So much like you may code a solution where you break it down into these small methods or small functions which do little pieces of the functionality of your application, by wrapping those in APIs, you can then continue to open that up. So not only can application 1 use method 1 in place A or place B, but application 2 can also start to leverage that functionality. So, if you consider that maybe task A is a geocoding service, and we know that we need to geolocate addresses in both application 1 and application 2, you can start to share that functionality by wrapping it in an endpoint, and then continue to share those results further up the food chain by leveraging those in web applications. So when we first started to approach this, we looked at using implementation entirely within the ArcGIS monolith architecture. So a user would come in using a UI built within React using Esri's ArcJS API. And then they would upload target locations that they were looking at. We would use a geocoding service to geocode those locations, make a request from the image server where those locations, where the aerial imagery of those locations were stored. And then PyTorch would evaluate those images and feed that back via REST endpoint to that React front. But I think almost immediately we started to experience some of the challenges that arose from taking this monolithic approach to implementing the model. So what were they? So first and foremost, and what really created most of the challenge, is that the REST call to the image server takes about 5 seconds on average to return the image. Why is this a problem? Well, single threading the execution, of course, blocks the image download. So no other functionality of the application can continue because of the single thread nature of this. So while you're waiting for that return to come from the server, the application can't proceed further. It can't do any other functionality. So you can multi-thread this. And by multi-threading it, you can allow, while you're waiting for a response from the server, other pieces of the functionality of that download can continue. There's a challenge with that, however, and that deployment of ArcGIS Pro, at the time especially, the ArcGIS Pro version of server, which is what was required for Python 3, and vis-a-vis required to have PyTorch be enabled on the geoprocessing service, was tricky, if not impossible, with multi-threading enabled. And so we were completely reliant here on single threading, which took up to 10 seconds per location. So by no means could that be considered real time if our user was waiting on a large job for 10 seconds. So what was the solution to this slowdown? So what I proposed here, and the solution that wound up being took, is to take a microservice approach to using ArcGIS technologies. So really it relies on 2 microservices, which are orchestrated by a Flask application. So that Flask application, Flask being one of the more commonly used web server tool sets for Python as a module. So that could function as an orchestrator with multi-threading enabled. And then by offloading the functionality which downloads the images, by offloading the functionality which geocodes the locations, we could multi-thread those calls. In so doing, while one image is being downloaded, the application can continue to download others and not have to wait those 5 seconds. So still the basic functionality is in place. We're still relying on a REST endpoint to interact with that React front end. We're still evaluating the model. We've just broken it up into those smaller constituent pieces, which can then have many, many threads thrown at them and same calls being executed at the same time. So what are the benefits here? Let's talk about it. So importantly, threads are non-blocking. If one thread takes 30 seconds, the rest continue. So if there's a delay in one of those endpoint calls, your application's not waiting for it. In the end, it may end up waiting for that one if it's prohibitively long, but in the near term, other threads can continue. Images can keep being downloaded even if one's taking longer than expected. You also have the ability to reuse the image preprocessor in other applications. If you have application B, which needs to use this same imagery, application B can now make the same endpoint calls to download those images and even multi-thread it. And importantly, that 10-second time frame to download one location was now reduced to an average execution time of just 1 second per location. So not only is that geocoding the locations, geocoding those addresses, it is downloading the image, it is doing all the pre-processing on the image, and then ultimately giving that to a PyTorch model to make those evaluations. All of that in under 1 second per location. So it was a really powerful tool, and it wound up speeding up the application about tenfold just by thinking about this in a different way and breaking this out into microservices. So finally, having put the microservices discussion behind us, I just want to take a few minutes and talk about the actual user interface, because the map is the compelling part, and it's the part that our partners in the National Catastrophe Center actually work with. So to them, all this code that's going on in the back end, everything that's enabling them to get these results so fast, it's irrelevant. It's a black box. But to them, what they see is this user interface, and I think that this is really where control of that application, where control of the where and the when and the how really occurs. So by creating this React.js interface with the JS API, we can create a user interface where the user can enter all of those parameters, where they can enter the locations that they're interested in looking at through drawing on the map. They can select the when and the how, and have that parsed into JSON and send that to that endpoint, which actually handles the model evaluation. So to them, they're seeing the search class in the JavaScript API, which allows them to quickly navigate to where they're interested at. We're using the imagery layer to show them the imagery. The map imagery layer, which allows for really the rapid display of hundreds of locations, which can be processed, as well as those stalwarts, the map and the view, which allow that to be represented on their screen. So as mentioned, they're able to go to this map interface and draw the area of interest that they want to look at, that they want to run the model at. They can draw that AOI, and in the backend, that's using the JS API's draw class, and then that user drawing is converted into a polygon, represented using a graphics layer on the user screen, but then sent using the coordinates back to that REST endpoint, which can process the job, telling that model where to run and what locations we're interested in here. So then using the submit button, they can then send that job, send that area of interest, send the dates they're interested in looking at. The application takes that, it processes it in the back end. In the back end, at this point, nothing is, or everything is happening in the back end rather. In the front end, nothing is really being shown to the user, but in the back end, that model's running, it's doing the heavy lifting. And in the back end, we're using that imagery service to serve images to the model and then evaluate it using PyTorch, so that open source module. And then finally, we can visualize those results. So point by point, those results come back to the user, and that client it parses that JSON response and then creates a graphic on top of it, showing each one of those points, each one of those locations, where there was a total loss as a result of wildfire. So it helps the users in our catastrophe center prioritize that, especially using the buttons on the side. So on the user interface's sidebar, there's these little house icons which allow the user to click on there and immediately pan and prioritize which locations they actually want to reach out to the customer for. So these are all sorted by likelihood of loss, so the probability that there was a total loss there. And And then all of these locations can be looked at, verified by the catastrophe team, and they can call the customer and reach out and help them to get paid faster, even if they in fact don't know that the extent of the damage was so bad because they've been evacuated and not able to get back to their home quite yet. So this all allows for faster identification and faster payment from us to our customers, and really helps the customer experience. So I've certainly covered a lot today and a lot of the application. I've given a pretty high level overview because more than anything, more than teaching folks how to code this, I wanted to really inspire to reframe the way that we think about things and how we operate within these cross-functional teams, because I think that it's the future of GIS within organizations, and I'm excited to talk about that and how we can provide smaller pieces of functionality that can help to drive larger initiatives within our organizations. So I just want to thank you again for taking the time to listen to this presentation and to kind of see what we did to approach this problem. Again, it was high level. I'm happy to answer any questions. Feel free to reach out to me via email. My email was at the beginning of the presentation. And feel free to add me on LinkedIn. Reach out on there as well. I'm always happy to talk with folks about the industry as a whole and the directions that the industry is going. So thank you again, and enjoy the rest of this the virtual Dev Summit. Thank you.